Physics textbooks are filled with unbreakable cosmic laws, but the universe loves to break them. From galaxies spinning impossibly fast to particles communicating instantly across vast distances, the cosmos is riddled with baffling anomalies that defy our deepest understanding. This journey will uncover 25 of the most profound instances where reality itself seems to ignore its own rulebook. You will discover what these cosmic rule breakers reveal about the true nature of existence, from the quantum realm to the edge of the observable universe. Why do stars on the outskirts of galaxies move with such unexpected speed? And what does a mysterious, never-repeated radio signal from the void tell us? These are not just scientific errors, they are clues pointing to a reality far stranger and more wonderful than we ever imagined. What do you think it means when the universe refuses to follow its own rules? Our first rule breaker drifted silently through the void for decades. The Pioneer 10 and 11 spacecraft, humanity's early messengers to the outer planets, carried with them a tiny, persistent secret. According to the unshakable laws of gravity laid down by Newton and refined by Einstein, their speed and trajectory were perfectly predictable. Yet, as these twin probes journeyed beyond Saturn, a faint, unexplained force was tugging them back. An anomalous deceleration, so small it was almost imperceptible, was slowing them down more than any calculation could account for. It was as if space itself had a bit more friction than anyone had ever dreamed. Imagine the bewilderment back on Earth. For years, scientists treated the anomaly like a cosmic detective story, chasing down every possible culprit. Was it a minute gas leak from the spacecraft's thrusters, giving them a tiny, unintended push? They checked. Was it the subtle pressure of heat radiating from the spacecraft's nuclear power source? They modeled it exhaustively. Every conceivable onboard explanation was investigated and ultimately ruled out. The drift was real. This left a profound and unsettling possibility. The discrepancy was not a mechanical error. It was a signal, a hint that our understanding of gravity itself, the very force that governs the cosmos, might be subtly incomplete when applied across such immense interplanetary distances. Some theorists wondered if the gravitational pull of unseen dark matter, woven through our solar system, could be the cause. Others proposed more radical ideas, suggesting that gravity might behave differently at the extremely low accelerations experienced by spacecraft on the fringes of our sun's influence. The Pioneer Anomaly became a quiet, decades-long reminder that our maps of reality are never truly finished. It taught us a humbling lesson. Even our most trusted physical models, the ones we write in textbooks and base entire missions upon, can harbor hidden surprises when we venture into new environments. That unexplained drift was more than just a navigational curiosity. It was a whisper from the universe, hinting at deeper layers of physics waiting just beyond our current understanding. While the Pioneer Anomaly was a subtle whisper, the next rule breaker was a cosmic shout. Look at a majestic spiral galaxy like our own Milky Way, a vast pinwheel of stars spinning in the void. According to the well-tested laws of gravity, this galactic dance should follow a predictable rhythm. Stars close to the bright, dense center, feeling the strongest gravitational pull, should whip around at tremendous speeds. But as you move outward toward the sparse, dark edges of the galactic disk, the stars should slow down considerably, just as the outer planets in our solar system orbit the sun more sluggishly than the inner ones. This is simple physics, or so we thought. The universe, however, had a different plan. When astronomers actually measured the orbital speeds of stars across entire galaxies, they found something impossible. The stars far out in the galactic suburbs were not moving slowly. They were racing around the center at nearly the same breakneck speed as the stars closer in. The rotation curve, as it is called, was flat. This was not just a small discrepancy. It was a fundamental rebellion against the laws of gravity as we understood them. The visible mass of a galaxy, all its stars and glowing gas, was simply not enough to generate the gravitational grip required to hold these speeding outer stars in their orbits. Without an immense, unseen source of gravity, these galaxies should have flown apart, their outer stars flung into the intergalactic void. The evidence for this cosmic defiance was cemented by the meticulous work of astronomer Vera Rubin. Her observations provided undeniable proof that something massive and invisible was at work, its gravitational pull governing the motion of stars. The only explanation that fit the data was the existence of a gigantic, unseen halo of dark matter enveloping each galaxy. This mysterious substance does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. It interacts with the ordinary matter we are made of only through gravity. This discovery was a profound shock. It meant that the glittering stars and glowing nebulae we see in every galaxy are just the visible frosting on a cosmic cake. The bulk of the universe's material, perhaps as much as 85% of all matter, is this invisible, unknown substance. We live in a universe dominated by a ghost, a shadowy architecture that holds the galaxies together while forever hiding from our view. If dark matter was the hidden hand holding galaxies together, another invisible force was preparing to tear the entire cosmos apart. For most of the 20th century, scientists believed they understood the ultimate fate of the universe. The immense gravitational pull of all the matter in the cosmos, from stars to dark matter, was expected to act like a cosmic brake, gradually slowing down the expansion that began with the Big Bang. The biggest question was whether that braking would be enough to eventually halt the expansion and pull everything back in a big crunch, or if the universe would simply coast forever, expanding at a slower and slower rate. Then, in the late 1990s, two independent teams of astronomers made a discovery that shattered this fundamental prediction. They were measuring the distances to extremely far-off supernovae, using these dying stars as cosmic mile markers to gauge how fast the universe was expanding in the distant past. They expected to see the expansion slowing down. Instead, they found the exact opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than any model of a slowing universe could account for. The data pointed to one inescapable and shocking conclusion. The expansion of the universe is not slowing down at all. It is speeding up. Galaxies are flying away from each other at an ever-increasing rate, as if some mysterious, repulsive force is stretching the very fabric of space itself. This discovery was so profound and so unexpected that it earned the teams the Nobel Prize in Physics in 2011. It meant that our universe is dominated by something even more bizarre than dark matter, a phenomenon scientists call dark energy. Think of it like this: if you toss a ball into the air, you expect gravity to slow it down and bring it back to Earth. But what if the ball, against all reason, shot away from you faster and faster into the sky? That is precisely what our universe is doing. This dark energy appears to be a property of empty space itself, a kind of anti-gravity that pushes galaxies apart. It makes up about 68% of the total energy and matter in the cosmos, completely overwhelming the gravitational pull of both normal matter and dark matter. This single observation rewrote the destiny of the entire cosmos. Instead of a potential big crunch or a gradual slowdown, the universe is now headed for a far more lonely and desolate end, a perpetual and accelerating expansion that will eventually pull all galaxies beyond the observable horizon of one another. The nature of this dark energy remains one of the greatest mysteries in all of science. Its discovery was a stark reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. If dark energy governs the vast cosmic stage, a far stranger drama unfolds in the microscopic quantum world. Here, particles can form a bond so intimate that it defies our most basic intuitions about space and distance. Two particles, perhaps born from the same event, can become inextricably linked or entangled. Their properties, like spin or polarization, remain in a hazy state of possibility until the moment one is measured. The instant you observe one particle and force it to choose a specific state, its distant partner instantly assumes a corresponding state, no matter if it is across the room or on the other side of the galaxy. This phenomenon is so counterintuitive that Albert Einstein himself was deeply troubled by it, dismissing it as spooky action at a distance. He believed it violated a core principle of physics known as locality, the idea that objects can only be directly influenced by their immediate surroundings. Nothing, not even information, can travel faster than light. Yet, entanglement seemed to suggest an instantaneous connection, a faster-than-light whisper between particles that mocked the cosmic speed limit. For decades, this was treated as a philosophical curiosity, a strange implication of the math that might not reflect real physics. Then came the experiments. Starting with the pioneering work of scientists like John Stuart Bell and continuing with ever more precise tests, researchers have confirmed that this spooky action is undeniably real. Entangled particles do influence each other instantaneously. This is not just a theory, it has been demonstrated repeatedly in laboratories around the world. How can this be? The truth is, we still do not fully understand the mechanism. It is not that information is traveling faster than light in a way we can use to send a message. Instead, it is as if the two particles are not truly separate entities at all, but two parts of a single, unified system. The vast space between them is, in a quantum sense, an illusion. This profound interconnectedness suggests that at its most fundamental level, reality may be woven together in a way that makes our classical ideas of separation and independent existence simply approximations, a convenient but incomplete story. The universe, it seems, is not a collection of isolated islands, but a single, deeply interconnected whole. This quantum spookiness hints at a deeper cosmic unity, but another paradox threatens to tear physics apart at the seams. Deep in the heart of a black hole, a war between two of our most successful scientific theories rages with no end in sight. On one side stands quantum mechanics, which presents a foundational rule for reality. Information, it declares, can never be truly destroyed. You can burn a book, turning its pages to ash and smoke, but in principle, a being with godlike knowledge could trace every particle and wave, reverse the process, and reconstruct every single word. The information is merely scrambled, never erased. On the other side stands Einstein's general relativity, which describes black holes as objects with such immense gravity that not even light can escape. They are, in the famous words of John Archibald Wheeler, black holes have no hair. This means that to an outside observer, a black hole can be completely described by just three simple properties: its mass, its electric charge, and its spin. Everything else about whatever fell in, the chemical composition of a star, the intricate pages of that book, the unique pattern of your memories, all of it is seemingly lost forever, scrubbed clean from the universe. For decades, physicists assumed this was just a strange feature of black holes, a one-way street to oblivion. Then Stephen Hawking made a startling calculation. He realized that due to quantum effects at the very edge of a black hole at its event horizon, these cosmic vacuum cleaners are not completely black. They slowly leak radiation, a faint glow of particles now known as Hawking radiation. This radiation carries away energy, which means the black hole slowly loses mass. Over immense stretches of time, a black hole will evaporate, fading away into nothing. And here lies the catastrophic paradox. When the black hole is finally gone, what happened to the information of all the things that fell into it? The Hawking radiation appears to be random, carrying no details about the black hole's contents. If it simply vanishes, then quantum mechanics is wrong, and information can be destroyed. But if quantum mechanics is right, then general relativity must be incomplete, failing to explain how the information gets out. This is the black hole information paradox, a fundamental crisis that has puzzled the greatest minds for half a century. Proposed solutions are as mind-bending as the problem itself. One leading idea is the holographic principle. It suggests that all the information about everything that falls into a three-dimensional black hole is not lost inside, but is instead perfectly preserved, encoded like a cosmic DVD on the two-dimensional surface of its event horizon. The three-dimensional interior we imagine is just a projection of that data. Another possibility is that the information does slowly leak out in the Hawking radiation, but in a form so scrambled and complex that we cannot yet decipher it. This paradox is more than a theoretical puzzle. It is a direct clash of titans, forcing physicists to confront the fact that our current laws of physics, while brilliant, are fundamentally incompatible when pushed to their extremes. Resolving it may require a new theory of quantum gravity, a framework that can finally unite the world of the very small with the realm of immense gravity, revealing a layer of reality where the very concepts of information and existence are rewritten. This cosmic conflict between quantum mechanics and gravity finds a strange parallel in the very structure of the universe itself, written in its oldest light. The afterglow of the Big Bang, the cosmic microwave background, paints a nearly perfect thermal blanket across the entire sky. In every direction we look, from one end of the cosmos to the other, this primordial radiation registers at almost exactly the same temperature, with only the tiniest of variations. This profound uniformity presents a problem of cosmic proportions, one we call the horizon problem. According to the standard Big Bang model, the universe simply has not existed long enough for heat to have traveled from one distant region to another to even out these temperatures. Think of it like this: you have 2 cups of coffee, one in New York and one in Tokyo. You want them to be the exact same temperature, so you need to mix them together. But if the only way for the heat to travel is at the speed of light, and you have not been given enough time for even a single photon to make the journey, how did both cups reach an identical chill? This is the puzzle of our cosmos. Regions of the universe on opposite sides of the sky have been flying apart since the beginning. They are so far apart that light, and therefore any influence or information, has not had nearly enough time to travel between them since the dawn of time. They exist beyond each other's cosmic horizons, forever out of touch. By all rights, they should have evolved independently, developing wildly different temperatures and properties. The fact that they are identical twins suggests they were once intimately connected, able to share energy and reach an equilibrium before being somehow torn apart. This paradox demanded a radical solution, and the most compelling answer is a concept known as cosmic inflation. The theory proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable ferocity. Space itself expanded faster than the speed of light, inflating from a subatomic speck to a volume far larger than our entire observable universe in less than a blink of an eye. This ultra-rapid expansion would have taken a tiny, previously connected patch of space that had already reached a uniform temperature and stretched it into the vast cosmos we see today. The regions that are now on opposite horizons were once neighbors, close enough to exchange energy and synchronize their conditions before inflation blew them apart. While inflation elegantly solves the horizon problem, it remains a theory, a powerful piece of the puzzle that explains one rule break but introduces new questions of its own. What could have powered such an explosive event, and why did it stop? This perfect thermal blanket we observe is a silent witness to the universe's most violent and mysterious infancy, a frozen echo of a moment when the very rules of expansion were rewritten. While the cosmic microwave background reveals a universe of stunning uniformity, a different kind of fossil points toward a different cosmic mystery. Deep within the oldest stars in our galaxy, astronomers have found a stubborn chemical discrepancy that challenges the story of our very origins. In the first few minutes after the Big Bang, the universe was a seething nuclear furnace, forging the first and simplest atomic nuclei in a process called Big Bang nucleosynthesis. Our models of this primordial cooking session are incredibly precise. They predict with remarkable accuracy the amounts of the lightest elements, hydrogen and helium, that we should see in the cosmos. The observations match these predictions almost perfectly, a triumphant success for the Big Bang theory. But there is one glaring exception, a single ingredient that refuses to follow the recipe. The models tell us that a specific isotope, lithium-7, should be about 3 times more abundant in these ancient stellar atmospheres than what we actually measure. It is as if a cosmic chef followed the instructions for a cake perfectly, measuring the flour and sugar exactly, but then deliberately used only a third of the eggs the recipe called for. This is the lithium problem. Where did all the lithium go, or was it never made in the amounts we think? For decades, scientists have wrestled with this puzzle. Could our understanding of the nuclear reactions in that first fiery furnace be subtly wrong? Perhaps exotic, unknown particles from the early universe interacted with the nascent nuclei, destroying lithium as it formed. Or maybe the ancient stars we use as cosmic time capsules are themselves processing the lithium over their long lives, somehow hiding it from our telescopes. None of these explanations has yet provided a definitive answer. This missing lithium is more than a small accounting error. It is a persistent, quantitative clue that our picture of the universe's first moments, while overwhelmingly successful, is not entirely complete. A fundamental piece of the cosmic origin story is still missing, lost in the faint light of the oldest stars. Even the empty voids between galaxies are not truly empty. They are filled with the faint afterglow of creation, the cosmic microwave background, a sea of ancient photons left over from the Big Bang. For the most energetic particles racing across the universe, this background radiation is not just a relic. It is a cosmic roadblock, according to a prediction made by physicists named Greisen, Zatsepin, and Kuzmin. Any proton traveling from a distant galaxy with an energy beyond a certain extreme limit, known as the GZK cutoff, should collide with these background photons. The impact would be so violent it would shatter the proton, sapping its energy long before it could ever reach Earth. The universe, it seemed, had imposed a strict speed limit on its most powerful cosmic rays. But the universe, as we are learning, loves to break its own rules. Giant observatories designed to catch these rare, high-energy particles have recorded something impossible. They have detected cosmic rays arriving from sources billions of light-years away, carrying energies far beyond the theoretical GZK cutoff. It is as if a marathon runner who should have collapsed from exhaustion miles ago not only finished the race but arrived at the finish line with more energy than when they started. These particles should not exist. Their very presence is a direct challenge to our understanding of particle physics. How did they make such an immense journey without being torn apart by the primordial light that fills all of space? One possibility is that we are wrong about the distances. Perhaps these ultra-high energy cosmic rays come from much closer, unknown sources within our own galactic neighborhood, powerful enough to fling them our way without a long, dangerous journey. But the data seems to point to origins in the distant cosmos. Another, more thrilling possibility is that our models of physics at these extreme energies are incomplete. Maybe there is a new type of particle or a strange interaction we have not yet discovered that allows these cosmic rays to cheat the universal speed limit. Or perhaps there are cosmic accelerators of unimaginable power lurking in the depths of space, far exceeding the ferocity of any supermassive black hole or colliding galaxy we know. These rule-breaking particles are more than just scientific anomalies. They are messengers from the farthest reaches of space and the highest energies possible, carrying encrypted clues about the fundamental laws that govern reality itself. Every one that strikes our atmosphere is a tiny, violent reminder that the cosmos still holds secrets about its own ultimate power. Yet another crack appears in the smooth facade of our cosmic foundations. The cosmic microwave background, that perfect thermal blanket, holds a secret pattern that makes cosmologists deeply uneasy. When scientists meticulously mapped the tiny temperature variations in this ancient light, they expected to find a random, symmetric distribution, like the static on an old television screen. The universe, according to the bedrock cosmological principle, should have no preferred direction. It should look the same everywhere and in every direction. But the data revealed something else entirely. The largest waves of hot and cold spots, the biggest temperature fluctuations, appear to be mysteriously aligned. Their orientation seems to correlate with the plane of our own solar system, a bizarre cosmic coincidence that has been nicknamed the axis of evil. Why such a dramatic name? Because if this alignment is real and not an illusion, it strikes at the very heart of modern cosmology. It suggests that our place in the universe might not be entirely random, that there is a preferred direction woven into the fabric of space-time itself. This is not a small statistical wobble. It is a potential crack in the cosmological principle, the core idea that the universe is isotropic and homogeneous on the largest scales. Imagine you walk into a vast, endless forest where the trees are supposed to be scattered in every direction with perfect randomness. But when you look around, you realize the very largest trees are all leaning in the same direction, and that direction just happens to point straight back to your own house. That is the unsettling feeling the axis of evil creates. Is it possible that we are somehow special, that our solar system's orientation is linked to the universe's largest structures? Most scientists are deeply skeptical, arguing it must be a statistical fluke or, more likely, contamination from something much closer to home. Perhaps the glow of dust within our own Milky Way galaxy is imitating this pattern, creating a foreground mask that we have not perfectly subtracted from the data. But despite years of analysis and more precise data from satellites, the anomaly stubbornly persists. It refuses to be washed away. This forces a profound and uncomfortable question. What if the universe is not the same in all directions? What if, on its grandest scales, it has a subtle grain, a fundamental anisotropy that gives it a preferred axis? The implications would be staggering, forcing us to rewrite our models of cosmic evolution from the very beginning. the axis of evil remains an unconfirmed but deeply troubling specter, a whisper that our universe might have a hidden architecture, a cosmic north that we have only just begun to sense. The universe's expansion rate should be a single, unwavering number, a cosmic drumbeat setting the tempo for everything. Yet two of our most trusted methods for measuring this fundamental constant are now telling two different stories, creating a rift at the very foundation of cosmology. When we look at the ancient universe using the cosmic microwave background as a fossilized echo of the Big Bang, we get one value for the Hubble constant. This method paints a picture of a cosmos expanding at a specific, predictable pace from its very beginning. But when we measure the modern universe using the brilliant flashes of nearby supernova and other local markers as our guide, we get a different, faster number. The contemporary cosmos appears to be expanding more quickly than its own ancient history says it should be. This growing discrepancy is the Hubble tension, and it is more than a simple measurement error. It is a direct conflict between the story of the universe's infancy and the reality of its present day. Imagine setting two incredibly precise atomic clocks at the moment of creation. You let one run for the entire age of the universe while you only check the other one today. When you compare them, they show different times. That is the profound level of contradiction we are facing. The early universe clock, based on the pristine conditions of the Big Bang, and the late universe clock, based on direct observation of today's galaxies, are ticking at irreconcilable rates. This forces a difficult choice. Either one of our methods contains a subtle, hidden flaw we have not yet uncovered, or our standard model of cosmology is missing a crucial ingredient. Perhaps dark energy is not a constant force but one that has evolved over time, strengthening its push. Maybe unknown types of neutrinos or other exotic particles flooded the early cosmos, altering its expansion history in a way we have not accounted for. Resolving the Hubble tension might mean we have to rewrite a chapter in our cosmic timeline, acknowledging that the universe's expansion has a more complex and dynamic story than we ever believed. This is not just a debate over numbers, it is a clue that our map of cosmic history from the first second to the present day may have a fundamental flaw hidden within its most trusted data. While the Hubble tension reveals a crack in our cosmic yardsticks, a far smaller measurement is causing an equally massive problem. We are now shrinking our focus from the vast expanse of the universe down to a single, fundamental particle, the proton. For decades, we thought we knew its size. The proton is a cornerstone of all matter, a building block of every atom in your body and every star in the sky. Its charge radius, the zone where its positive electric charge is distributed, was considered a fixed, knowable number. We measured it in two primary ways. One method involved firing electrons at protons and watching how they scattered, like using a high-speed pellet to probe the shape of a hidden target. The other method used the hydrogen atom, studying the delicate energy levels of its single electron orbiting a single proton. Both methods, refined over many years, seemed to agree, giving the proton a comfortable, well-defined size. Then, around the year 2010, physicists tried a new, incredibly precise technique. Instead of using a regular hydrogen atom with an electron, they created muonic hydrogen. A muon is a particle identical to an electron in every way except it is 200 times heavier. This greater mass means the muon orbits much closer to the proton, acting as an exquisitely sensitive probe of the proton's internal structure. By measuring the subtle shifts in the muon's energy levels, scientists could calculate the proton's charge radius with unprecedented accuracy. The result was a shock. The proton measured in muonic hydrogen was significantly smaller, by about 4%, than the value obtained from all the previous electron-based experiments. 4% might sound tiny, but in the world of subatomic precision, it is a Grand Canyon-sized discrepancy. It is far larger than the margin of error in any of the experiments. This is the proton radius puzzle. How can the same particle have two different sizes depending on how you measure it? This is not just a case of better tools giving a more precise number. It is a fundamental conflict. One possibility is that our most trusted theory, quantum electrodynamics, which describes how light and matter interact, is somehow wrong, but only when heavy muons are involved. This seems unlikely, as the theory has passed every other test with flying colors for decades. A more thrilling possibility is that we are seeing the signature of new physics. Perhaps an unknown fifth fundamental force of nature is at work, a force that only interacts with muons and not with electrons, subtly altering the energy levels in muonic hydrogen and skewing our measurement. Or maybe there is something about the proton itself that we do not understand, a strange internal dynamic that only reveals itself to the heavier, more intimate touch of a muon. This tiny anomaly in a single particle size sends ripples through all of physics. The proton is not some exotic object, it is the heart of the atom. If we have misunderstood something so basic, what else have we overlooked? The proton radius puzzle proves that sometimes the biggest secrets are hidden not in the distant cosmos, but in the infinitesimal space within the particles that make us who we are. While we struggle to measure the size of a single proton, our largest spacecraft are being toyed with by an unseen hand. On their way to distant destinations, probes like Galileo and NEAR have used Earth's gravity as a slingshot, a carefully calculated maneuver to steal a little orbital energy and boost their speed. The math for these flybys is a masterpiece of precision, factoring in our planet's mass, its rotation, and the subtle pull of the Moon. Yet, on multiple occasions, as these spacecraft whipped around our world, they emerged with a tiny, unexpected bonus or deficit in their velocity. The change was minuscule, often less than a few millimeters per second, but it was undeniably real and consistently unaccounted for. It was as if the universe was adding a mysterious, unplanned tax or reward to every gravitational transaction. This is the Fly-by Anomaly, a small but persistent glitch in the cosmic code. Each event was a perfect puzzle. The Galileo spacecraft, on its way to Jupiter, gained about 4 millimeters per second more speed than predicted. The NEAR Shoemaker probe, headed for an asteroid, experienced a gain of nearly 13 millimeters per second. These numbers sound trivial, but for mission controllers navigating across billions of miles of space, such errors can mean missing a target by thousands of miles. Every conventional explanation was scrutinized. Was it the gentle push of radiation pressure from the sun, they checked? Could it be the drag from Earth's faint outer atmosphere? The altitude was far too high. What about the gravitational influence of the tides or even the planet's uneven mass distribution? Our models are too good. None of these could explain the discrepancy. The most tantalizing proposals point toward the edges of Einstein's general relativity. Perhaps the rotating Earth is dragging the fabric of space-time around with it, an effect known as frame dragging, but the measured influence is far too weak to explain the anomaly. Others have wondered if there is a hidden component to gravity itself, a subtle, longer-range effect that only becomes noticeable during these very specific, high-velocity planetary encounters. It is as if gravity has a secret clause in its contract that we have not yet read. These fly-by anomalies are not dramatic, universe-shattering events. They are whispers, faint fingerprints left on our machines by a force we have not yet named. They remind us that even our most trusted celestial mechanics, the physics we use to send robots to other worlds, might be based on a map that is ever so slightly incomplete. Each unexpected millimeter per second is a question mark written in motion, a hint that the pull of a planet holds secrets we are only just beginning to sense. Our cosmic background radiation holds another chilling secret, a patch of sky so profoundly cold it defies simple explanation. This is the cold spot, a region in the constellation Eridanus that is far colder and vastly larger than any standard model of the universe can comfortably account for. Imagine the afterglow of the Big Bang as a canvas of subtle warmth painted with tiny, random variations. The cold spot is not a mere brushstroke. It is a gaping hole in that canvas, an immense and unexpected chill. If the universe's structure is a symphony of random fluctuations, this cold spot is a dissonant chord that rings out with unsettling volume. It is not just a little bit colder. It is a colossal anomaly stretching over 1 billion light-years across, a cosmic supervoid of such staggering size that its very existence should be statistically almost impossible. How could such a vast and empty region form? One leading theory is that it is exactly that, an immense cosmic void, a bubble of near nothingness in the cosmic web. In such an empty region, photons from the cosmic microwave background would have to climb out of a deeper gravitational well, losing energy and thus appearing colder to our telescopes. But the scale of the void required to produce this effect is so enormous that it challenges our understanding of how structure forms in the universe. It would be a void among voids, a true outlier. An even more radical proposal suggests this chill is not from a void within our universe, but from something outside it. The cold spot, some physicists argue, could be a bruise, a cosmic imprint left by a collision with another universe in the vast multiverse. In this breathtaking scenario, the energy drained from that long-ago collision with a separate bubble of reality could have left this permanent cold mark on our sky. Whether it is a staggering emptiness or a scar from a parallel cosmos, the cold spot stands as a direct challenge to the standard cosmological model. Its statistical significance is too great to ignore, a stark reminder that the largest structures we observe might be governed by processes we have not yet dreamed of. This frigid patch is more than a curiosity. It is a potential window, a place where the fabric of our reality might be thin enough to see the shadows of what lies beyond. Far out beyond the orbit of Neptune, the solar system was supposed to have a gentle, fading finale. The Kuiper belt, a vast disk of icy worlds and frozen debris, should have thinned out slowly, like a crowd dispersing after a concert. Yet when astronomers began to map this distant realm, they found something completely different. The belt does not fade away, it ends. At a distance of about 50 astronomical units from the Sun, there is a stark and unexpected boundary, a cliff edge in space where the population of objects plummets to almost nothing. This is the Kuiper Cliff, a sudden stop sign at the edge of our known planetary system. Why does this frozen frontier have such a sharp and definitive edge? A gradual decline would be natural, but this is a precipice. It is as if you were walking through a forest that was steadily thinning, and then you stepped into an absolute, perfectly cleared field that stretched on for miles. The most straightforward models of solar system formation cannot explain it. Something must be actively sweeping that region clean, or it was never populated in the first place. One compelling hypothesis points to the gravitational pull of an unseen giant planet, a so-called Planet 9, lurking in the darkness far beyond the cliff. This hypothetical world, with a mass several times that of Earth, could have carved out this emptiness over billions of years, its immense gravity kicking out any smaller objects that ventured into its domain. Another possibility reaches back into the Sun's ancient past. Perhaps our star was born in a dense cluster alongside other stars, and a close flyby from a sibling star in that long-vanished nursery stripped away the outer Kuiper belt, stealing its material and leaving behind this stark boundary. Both ideas are profound. One suggests our solar system is still hiding a major world, a ghost planet whose subtle influence we are only now detecting. The other implies that our system's architecture was permanently scarred by a dramatic stellar encounter in its infancy. The Kuiper Cliff is more than just an empty zone, it is a fossilized border. Its existence tells us that the story of our solar system's formation is not yet fully written, and that its outermost reaches hold clues to violent historical events or massive, unseen actors still waiting in the wings. Deep in the silence between the stars, a single, perfect sound once rang out. On a late summer evening in 1977, a radio telescope at Ohio State University known as the Big Ear was carrying out its routine survey of the sky. It was a volunteer astronomer, Jerry Amon, who was later reviewing the computer printout of the data when his eye caught a sequence of letters and numbers so extraordinary that he circled it in red pen and wrote one word beside it: "Wow." The signal had lasted for 72 seconds, the exact duration the telescope could hold a fixed point in the sky. It was a powerful, narrowband radio burst, concentrated on one specific frequency, the hydrogen line, which scientists had long speculated would be a logical channel for interstellar communication. It came from the direction of the constellation Sagittarius, and then it was gone. This was not the random hiss of a quasar or the messy broadband crackle of a passing satellite. It was a clean, artificial-sounding beacon, exactly what we would expect to hear if an intelligent civilization was aiming a transmitter our way. The hunt began immediately. Astronomers pointed every available dish toward that patch of sky, listening for a repeat, for a pattern, for anything. They searched for years and then for decades. They found nothing. No natural phenomenon we know of can easily explain it. It was not a passing aircraft or a reflection from a piece of space debris. It did not match the signature of any known cosmic event. The WOW signal remains a perfect, solitary mystery, a one-night stand with the cosmos. Its transient nature is what makes it so profoundly challenging. Natural astrophysical events like stellar flares or collapsing stars usually leave some kind of afterglow or a repeating signature. This was a single, brilliant flash in the radio pan, a cosmic shout that has never been uttered again. It forces us to confront a tantalizing and humbling possibility. The universe might be filled with ephemeral signals, brief and brilliant windows of contact that open for a moment and then close forever. Was it a one-time beacon from a long-dead civilization, its message just now reaching us? Could it have been an immense, natural laser pulse from a random stellar alignment, a freak event of cosmic proportions that we have never been lucky enough to witness a second time? The signal's very elusiveness is its power. It stands as a monument to the idea that our search for cosmic company is not just a matter of patience, but of perfect, unpredictable timing. We are listening for a whisper in a hurricane, and for one unforgettable minute we may have heard it. Deep within the heart of every atom, a delicate balance of power keeps the universe from flying apart. The strong nuclear force binds protons and neutrons together in the nucleus, but this glue only works when paired with the stabilizing presence of positively charged protons. A nucleus made of neutrons alone should be an impossibility, a house of cards collapsing before it can even form. Yet, in a series of startling experiments, physicists may have caught a fleeting glimpse of exactly that, a ghostly particle that should not exist. They call it the tetraneutron, a cluster of 4 neutrons bound together with no protons at all. Its existence, if confirmed, would shatter a foundational pillar of nuclear physics. The Pauli exclusion principle, a fundamental quantum law, states that no two identical fermions, like neutrons, can occupy the same quantum state. This principle is what gives matter its structure and prevents it from collapsing into itself. For four neutrons to form a stable cluster, they would have to somehow sidestep this rule, finding a loophole that allows them to coexist in a way our current theories say is forbidden. The evidence for the tetraneutron is tantalizing but not yet conclusive. It appears as a brief, resonant signal in high-energy collision experiments, where scientists smash atomic nuclei together and sift through the subatomic debris. In that chaos, they have spotted a signature consistent with a four-neutron entity that lives for just a sliver of a second before it decays. That minuscule lifespan is enough to send shockwaves through the field. How could such a structure hold itself together, even momentarily, without the balancing charge of a proton? Our models of the nuclear force have no comfortable place for it. This potential particle is more than a laboratory curiosity. It forces us to ask profound questions about the nature of matter under extreme conditions. If neutrons can form stable clusters on their own, what does that mean for the core of a neutron star, an object so dense it is essentially a giant atomic nucleus the size of a city? The intense gravity there crushes atoms together, squeezing out electrons and protons to create a sea of neutrons. The tetraneutron suggests that this sea might not be uniform, but could be lumpy, forming strange, temporary islands of pure neutron matter with properties we can barely imagine. It could even alter our understanding of how heavy elements are forged in the violent aftermath of colliding neutron stars. The tetraneutron stands as a ghost at the feast of nuclear physics, a hint that the rules governing the building blocks of reality might be far more flexible and far stranger than we ever supposed. The desire to shatter the speed limit of space travel has led to one of modern physics' most contentious debates. In a laboratory, a device shaped like a hollow, truncated cone sits inside a vacuum chamber. When microwave energy is bounced around inside this metal cavity, something unbelievable seems to happen. The entire apparatus appears to generate a tiny, persistent thrust, pushing ever so slightly in one direction. This is the M drive, and its claim is a direct assault on a fundamental law, the conservation of momentum. For centuries, we have known that every action must have an equal and opposite reaction. A rocket works by violently expelling propellant out its back, and the recoil pushes it forward. You cannot move a car forward by sitting inside and pushing on the dashboard. Yet the M drive claimed to do the cosmic equivalent, creating thrust from nothing, a push with no apparent pushback. The scientific community reacted with deep and rightful skepticism. How could a closed system generate net force without expelling any reaction mass? It seemed to be getting something for nothing, a perpetual motion machine for the space age. The thrust measurements were infinitesimally small, and critics argued they were almost certainly the result of experimental error. Perhaps heat expansion in the device was creating subtle movements, or the Earth's magnetic field was exerting an unseen influence. Maybe the thrust was an artifact of the measurement apparatus itself. Study after study attempted to replicate the results, with some teams reporting a faint, positive signal and others finding nothing at all. The controversy raged for years, a perfect storm of public fascination and scientific rigor. The allure was undeniable, an engine that needed no fuel. It promised to revolutionize space exploration, turning journeys to Mars into routine trips and making the stars themselves seem within reach. This dream, however, collided with the hard wall of established physics. The saga of the M drive is a masterclass in how science grapples with revolutionary claims. The process is slow, messy, and often frustrating. Extraordinary claims require not just extraordinary evidence, but bulletproof, repeatable evidence that can survive the scrutiny of the entire global scientific community. In the end, the most likely explanation for the M-drive's observed thrust is a combination of subtle, unaccounted for experimental errors. But to dismiss this story as a simple failure is to miss its deeper meaning. The very fact that such an idea was taken seriously enough to be tested in multiple labs around the world speaks to our burning desire to find a crack in the cosmic rulebook. The M-drive, even as a beautiful mistake, represents the relentless human impulse to ask, what if the universe allows a shortcut? That hunger to challenge the impossible is the same force that has propelled every great discovery, reminding us that the path to rewriting physics often begins with a brave and sometimes wrong idea that dared to break a rule. While the M-drive controversy tested the limits of known physics, a far more meticulous experiment was uncovering a genuine crack in the foundations. Deep beneath the Illinois prairie, at the Fermi National Accelerator Laboratory, physicists were not chasing speculative thrusters. They were measuring a fundamental property of a particle with painstaking precision, and the universe answered with a tiny, undeniable whisper of something new. Their subject was the muon, the heavier, unstable cousin of the electron. Like a child's spinning top, every muon possesses an inherent spin, and with that spin comes a tiny magnetic field, a property known as its magnetic moment. The strength of this magnetism is represented by a value called the G-factor. For decades, the standard model of particle physics, our most successful theory of the subatomic world, has allowed physicists to calculate this G-factor with breathtaking accuracy. The math is a masterpiece of quantum complexity, accounting for the muon's interactions with a cloud of virtual particles that constantly pop in and out of existence around it. According to the rulebook, the calculated value and the measured value should match perfectly. They do not. In an experiment called Muon G2, scientists store these unstable particles in a perfectly uniform magnetic field, watching their spin precess or wobble like a gyroscope. The rate of this wobble reveals the strength of its internal magnet. After years of collecting data from billions of muons, the results are in. The muon's wobble is ever so slightly faster than the standard model predicts. This is not a margin of error, it is a persistent, statistically significant anomaly. What could be causing this? The leading hypothesis is as thrilling as it is profound. The muon might be feeling the subtle influence of entirely new particles or forces not included in our current cosmic inventory. That cloud of virtual particles flickering around it may contain more than just the known cast of quarks and photons. It could be teeming with ghostly partners predicted by theories like supersymmetry, or harboring carriers of a hidden fifth force. This tiny discrepancy in a muon's dance is like hearing a perfect, familiar symphony, but with one extra, faint instrument playing a note that does not belong. You cannot see the musician, but you can unmistakably hear its sound. The implications are staggering. For over half a century, the standard model has stood as a fortress, resisting all challenges. It has correctly predicted the outcomes of countless experiments, yet it is famously incomplete. It cannot explain dark matter, dark energy, or the force of gravity itself. The Muon G2 anomaly is the fortress wall showing its first real crack. It is a direct signal that the subatomic zoo is not yet complete, that there are more actors waiting in the wings of reality. This is not the end of the story, but a compelling new beginning. The hunt is now on to find the source of this magnetic mischief, to pinpoint the new physics that must be lurking just beyond the edge of our current understanding. Even our most basic cosmic inventory is shockingly incomplete. We thought we had a firm grasp on the ordinary matter, the atoms and molecules that build everything we can see and touch, from the planets to the stars to our own bodies. Yet when astronomers tally it all up, from the present-day universe back to the dawn of time, the numbers do not match. The amount of normal matter we detect in the nearby cosmos is only about half of what the Big Bang theory predicts should be there. This is the missing Baryon problem, a cosmic accounting error on a galactic scale. It is as if you carefully counted all the cash in your wallet, but your bank statement showed you had twice as much money, with no record of where the rest had gone. These missing baryons are not some exotic dark matter. They are the very stuff we are made of. So where did half the atoms in the universe go? The leading suspect is a vast, diffuse web of superheated gas, a cosmic plumbing system known as the warm-hot intergalactic medium. Picture this not as a cloud, but as immense, thread-like filaments of incredibly hot, ionized gas stretching between galaxies, forming the skeleton of the cosmic web. This gas is so hot it glows not in visible light, but in far ultraviolet and low-energy X-rays, and it is so thin that a single cubic meter of it might contain only a few atoms. Detecting it is like trying to see the heat shimmer rising from a single candle from miles away in a fog. Finding this hidden reservoir is not just about solving a puzzle. It is absolutely crucial for validating our entire standard model of cosmology. The model tells us precisely how much ordinary matter was forged in the Big Bang. If we cannot find it all, it means we fundamentally misunderstand where and how the basic building blocks of reality are stored. This cosmic hide-and-seek game forces us to develop new eyes, to build telescopes sensitive to the specific energies of these faint intergalactic filaments. Each time we find a new strand of this hidden web, we are not just locating missing atoms, we are confirming the grand architecture of the universe itself, proving that even the most ordinary stuff can master the art of invisibility. Our planet's own history holds a climate mystery that defies the laws of stellar evolution. Billions of years ago, our sun was a faint, young star, shining with only about 70% of the brightness it has today. According to every reliable climate model, that weaker sunlight should have left the entire Earth as a global snowball, a frozen wasteland locked in ice from pole to pole for its first 2 billion years. The rocks, however, tell a completely different story. The most ancient geological evidence we have, from zircon crystals to sedimentary formations, clearly shows that liquid water was abundant on the surface. Rains fell, rivers flowed, and vast oceans stretched across the globe. Earth was not only unfrozen, it was a temperate world, a cradle for the very first stirrings of life. How could a planet stay warm under a dimmer sun? This is the faint young sun paradox, a direct contradiction between our understanding of stars and the hard evidence written in stone. The only logical solution is that something else was warming the young Earth, creating a powerful greenhouse effect that compensated for the lack of sunlight. Our atmosphere must have been drastically different, likely filled with far higher concentrations of heat-trapping gases like methane and ammonia, or perhaps even carbon dioxide, creating a thick, insulating blanket. Another possibility is that the planet itself was darker, with less reflective ice and land, absorbing more of the feeble solar energy that did arrive. Some scientists have even proposed that a stronger gravitational interaction with the Moon created more intense tidal heating, or that the Sun itself had a more active and warming stellar wind. Whatever the answer, this ancient climate puzzle is not just about our past. It is a vital key to understanding the delicate balance that makes a world habitable. If we cannot explain how Earth remained warm then, how can we truly trust our models for predicting climate change now, or for assessing whether distant exoplanets orbiting other stars could hold life? The faint young sun paradox reminds us that a planet's climate is a complex, dynamic system, capable of finding stability in ways we are only beginning to comprehend. A silent river of galaxies, including our own, is flowing against the cosmic tide. While dark energy pushes the universe apart on the grandest scales, a mysterious and immense gravitational force is pulling us, along with millions of other galaxies, toward a specific point in the void. This cosmic current moves at an astonishing speed of over 600 kilometers per second, all directed at a patch of sky obscured by the dusty heart of our own Milky Way. We call this unseen monster the Great Attractor. It is a gravitational anomaly of staggering proportions, a place where the mass of 500,000 Milky Ways is concentrated, creating a pull so strong it overrides the universe's expansion in our local neighborhood. Think of it like a vast cosmic whirlpool. The Hubble flow is the outgoing tide, but within this local basin, the gravitational current of the Great Attractor is a powerful undertow, dragging everything toward its hidden center. For a long time, its true nature was a mystery because it lies directly behind the zone of avoidance, a region of the sky where the gas, dust, and stars of our own galaxy's central bulge block our view. It is like trying to see a distant city while standing in a dense, foggy forest. We could feel its immense pull, but we could not see what was causing it. Modern X-ray and radio telescopes, which can peer through the galactic dust, have revealed that the Great Attractor is not a single, impossible object. It is the heart of the Laniakea supercluster, a vast cosmic metropolis of over 100,000 galaxies to which our Milky Way belongs. We are not falling into a single black hole or a dark overlord. We are being drawn toward the collective gravitational center of this immense structure, a grand focal point in the cosmic web. This discovery reshapes our cosmic address. We do not just live in the Milky Way, which is part of the local group, which is itself a tiny part of the Virgo supercluster. We now understand that the Virgo supercluster is merely an arm of the far greater Laniakea, and we are all flowing toward its gravitational core. The Great Attractor is a profound reminder that the universe is not a uniform, expanding balloon. It is a dynamic, lumpy, and textured place where the gravitational pull of immense structures can create local currents that defy the overall expansion. We are not passive passengers on a drifting raft, but active participants in a grand gravitational dance, pulled toward a center we can only now begin to map. The very geometry of cosmic expansion is now under a subtle but powerful observational siege. We have long accepted that the universe is stretching, a fact supported by the redshift of distant galaxies. But a century-old test conceived by physicist Richard Tolman offers a unique way to verify this expansion, not by the color of the light, but by its inherent dimness. The Tolman surface brightness test makes a precise prediction. In a truly expanding universe, the surface brightness of a galaxy, its glow per unit area, should fade dramatically with distance, decreasing with the fourth power of its redshift. Think of it like a street lamp on a foggy night. As you move away, not only does the lamp appear fainter overall because the light has farther to travel, but the very patch of light it illuminates on the fog also grows larger and more diffuse. The expansion of space acts like that cosmic fog, stretching the light and diluting its intensity in a very specific, predictable way. Yet, when astronomers perform this test on the most distant elliptical galaxies, some studies find a puzzling result. The dimming is not as severe as the expanding universe model demands. The galaxies appear just a bit too bright for their colossal distance. It is as if that distant street lamp, against all expectation, is holding its glow a little too well. This is not a small discrepancy. If confirmed, it strikes at the core of modern cosmology. One radical interpretation is that the universe is not expanding at all, and that redshift is caused by some other, unknown physical process, a possibility that would overturn a century of established science. A more likely, yet still profound, explanation is that our measurements of cosmic distance are systematically flawed. Perhaps our understanding of how light interacts with interstellar dust or the intrinsic properties of ancient galaxies is incomplete. The Tolman Test is more than a technical check. It is a direct probe into the geometry of reality itself. A confirmed deviation would mean that the fabric of space-time is woven in a way we have not yet anticipated, forcing a rewrite of the cosmic expansion story we thought we knew. Sometimes the most profound mysteries arrive not from deep space but from our own stormy skies. In 1753, the Russian physicist Georg Richman set out to measure the electrical charge of a thunderstorm, a daring experiment for its time. As he reached toward his apparatus, a glowing sphere of fire, described as a fist-sized ball of blue light, traveled down the wire, struck his forehead, and killed him instantly. This was not a normal lightning strike. Witnesses described a persistent, floating orb, a phenomenon we now call ball lightning. Richman may have been the first scientific casualty of a rule breaker that still defies explanation today. These strange spheres of light appear during thunderstorms, often drifting through the air, passing straight through walls or windows as if they were ghosts. They can hover for several seconds before vanishing silently or sometimes with a violent pop. According to everything we know about plasma physics, this behavior is impossible. A ball of plasma should dissipate in a fraction of a second, not float serenely through a room. Its sustained energy and ability to penetrate solid matter suggest a form of matter or a contained energy state that our current models cannot describe. What could possibly hold such a thing together? One theory suggests these orbs are not pure plasma at all, but a vaporized silicon aerosol created when lightning strikes the soil, organizing itself into a glowing, stable structure. Another, more exotic idea proposes they are miniature knots of magnetic energy, or perhaps even contain a bizarre, high-energy vacuum state. Each observed ball is a tiny, temporary rebellion against the known laws of electromagnetism and thermodynamics, a pocket of reality operating on its own secret rules. These fleeting atmospheric anomalies are more than just curiosities. They are direct, observable evidence that even in our own familiar atmosphere, there are pockets of physics we have not yet mapped, forms of energy that dance just beyond our understanding, appearing only for a moment to remind us that the universe's rulebook is far from complete. Our own galactic neighborhood presents a structural puzzle that defies our best simulations. The Milky Way is not alone. It is surrounded by a retinue of smaller satellite galaxies, cosmic minions orbiting our grand spiral. According to the standard model of cosmology, these satellites should be distributed randomly around us, like flies buzzing around a lamp in a dark room. They should swarm in a roughly spherical cloud, each following its own independent and chaotic orbit, a legacy of the random way dark matter halos are thought to assemble. But when astronomers mapped their precise positions, they found something completely different. A significant number of these dwarf galaxies are not scattered randomly at all. Instead, they are aligned with breathtaking precision in a vast, thin, rotating disk, a structure known as the vast polar structure. This is not a slight statistical preference. It is a stark geometric arrangement, a cosmic carousel of galaxies spinning in a plane that cuts across the Milky Way. The probability of this happening by pure chance in our established dark matter models is astronomically low, like throwing a handful of confetti into the air and having it land in a perfect spinning circle. This organized dance presents a profound challenge. It suggests that the process of galaxy formation is far more structured and dynamic than our simulations predict. One compelling explanation is that these satellite galaxies are not primordial captives at all, but the torn apart remains of a single, larger galaxy that collided with and was cannibalized by the Milky Way in the distant past. In this violent merger scenario, the debris would naturally be strung out along a coherent orbital plane, much like the scattered pieces of a broken string of pearls would continue to trace out the original path. This would mean our galaxy's history is written in the organized motion of its satellites, a fossil record of a long-ago cosmic feast. If this is not the case, and these dwarfs are indeed primordial, then our understanding of how dark matter clumps and guides the growth of structures must be fundamentally flawed. The existence of this plane forces us to reconsider the very architecture of our home galaxy and the invisible scaffold of dark matter that shapes it. The satellites are not just random followers, they are a chorus singing in unison, and their coordinated song tells a story of either a violent past or a hidden order we are only beginning to hear. Even the universe's oldest light holds a subtle but profound flaw in its grand design. The cosmic microwave background is not perfectly smooth, and those tiny temperature fluctuations are a treasure map of the cosmos's infancy. Yet when scientists analyze the very largest patterns in this map, the ripples that stretch across almost the entire observable universe, they find something deeply puzzling. The biggest waves, known as the quadrupole moment, are far weaker than our most trusted models say they should be. The universe appears to be surprisingly smooth on its grandest scales, as if someone turned down the volume on the cosmos's deepest bass notes. This lack of large-scale power is more than a statistical hiccup. It is a persistent whisper that our reality might be smaller or stranger than we think. Why would the largest possible structures be so suppressed? One breathtaking possibility is that the universe is not infinite. It could be finite, but wrapped in on itself in a way that limits how large any fluctuation can grow, like the patterns on a soccer ball that can only get so big before they meet themselves. This would mean that if you could travel far enough in a straight line, you might not journey forever into an endless void, but eventually return to your starting point from another direction. Another explanation points to the very mechanism of inflation, the universe's explosive initial growth spurt. Perhaps inflation did not proceed in the standard way we assume, and its unique dynamics left the cosmos with this unexpected large-scale calm. This anomaly has stubbornly persisted for decades, surviving through ever more precise data from satellite missions like COBE, WMAP, and Planck. Each new, higher-resolution map of the infant cosmos has confirmed the same curious quiet at the very largest scales. This is not an error that has been resolved, it is a feature of our reality that has been reinforced. The low quadrupole is a ghost in the machine of cosmology, a subtle clue written across the entire sky that the global properties of our universe, its true shape and size, might be fundamentally different from the infinite, featureless expanse we often imagine. This large-scale smoothness is a quiet challenge to our cosmic assumptions, a faint signature that the greatest stage of all may have hidden walls, a secret geometry, or an origin story we have not yet fully read. Together, these 25 cosmic anomalies form a single, undeniable message. Our universe is not a simple machine governed by a handful of elegant equations. It is a living, breathing puzzle box of immense complexity, a multi-layered reality where our current laws are merely the first, rough draft. Every one of these rule breaks, from the impossible spin of galaxies to the missing lithium in ancient stars, is a crack in the facade of our understanding. And through those cracks we glimpse a far grander and more mysterious cosmos. These are not failures of science, They are its greatest triumphs, the moments when nature itself taps us on the shoulder and points toward a deeper truth. They reveal the profound limitations of our own perception. The laws of physics we hold so sacred, the ones written in every textbook, may only be provincial bylaws, perfectly valid for our little corner of the cosmos, but utterly incapable of describing the whole. Think of it like a fish that has only ever known its own pond. It might devise perfect laws for pond life, governing currents and temperatures, completely unaware of the vast ocean just beyond the river bend. Our situation is strikingly similar. These puzzles are the irresistible force that drives all scientific progress. They are the reason we are compelled to invent radical new ideas. Without the galaxy rotation problem, we would have no concept of dark matter. Without the horizon problem, the theory of cosmic inflation would never have been born. Without the black hole information paradox, we would not be so desperately searching for a theory of quantum gravity. Each anomaly is a fertile ground for revolution, a place where old certainties die and new, more powerful visions of reality can take root. To truly understand the cosmos, we must not fear these mysteries. We must embrace them. They are the universe's way of teaching us, of showing us where our maps are blank. The journey to a truer understanding of reality begins not with the answers we already have, but with the courageous admission of everything we do not know. Our journey through these 25 cosmic rule breaks reveals a universe that is wonderfully, bafflingly inconsistent with our textbooks. From the quantum realm to the cosmic horizon, each anomaly we have encountered is a direct challenge to our most cherished assumptions, forcing us to push the boundaries of knowledge ever further. These are not mere errors in measurement or simple gaps in our data. They are profound clues scattered across the cosmos, each one pointing toward a grander and more intricate reality waiting to be discovered. Every time a galaxy spins too fast, a particle communicates instantly, or a signal appears from nowhere, the universe is handing us a piece of a puzzle we are only beginning to assemble. As we continue to probe the cosmos with ever more powerful tools and ever more daring ideas, we must remember a fundamental truth. Every broken rule is not a failure of our understanding, but a fertile opportunity for a revolutionary breakthrough. The universe, in its infinite complexity, is not just stranger than we imagine. It may very well be stranger than we can imagine. Which of these cosmic anomalies fascinates you the most? Was it the ghostly pull of dark matter, the spooky connection of quantum entanglement, or the lonely perfection of the wow signal? Share your thoughts in the comments below and subscribe for more deep dives into the endless mysteries of space.